Welcome back to the course. So before we begin, like few quick announcements. I think the grade scope is not yet open. Like I will make sure that the field open it today. So the assignment is due next week, right? Is that right? Yeah. So the assignment is due next week, and if you still have not signed up in grade scope, do it immediately. And also, it seems not all of you have signed up with Piazza. So Piazza is where you can ask your questions and like, well, you can go to office hours, of course, like, but if you want to talk to others in the class through conversations, like, Piazza is a good medium. So register in Piazza and grade scope. But I should not be saying this on the 4th week. It's already too late. So if you haven't done so, do it. And we did not have trial assignment in this course, actually. Sorry, like, which means you have to be careful when you're submitting your first assignment. Like, so if you have never used Gradescope before, like, you have to tag each question in the PDF. So don't keep it to the last 1 hour of the assignment deadline. So try to do it at least a couple of days before once. You can update it as many times as you want. So try to do it once so that you know how to do it. And also, we often receive questions about where is the video for the, or where is the recording for the course. Like, so we gave the link and made an announcement in the initial, for the first week, but we don't do announcements every week. Like, so, like, but the lectures are automatically, well, not automatically, but we process it and it is uploaded in the same YouTube channel, probably a day or two after the lecture. Most often on the same day of the lecture, like probably tonight, right? So, like, if you want to get notifications, you should just subscribe to that YouTube channel, like, so which is where I put both ML and RL lectures, like, so that you get notified whenever there is a new video which is uploaded. So this is one of the most common questions that me and PAs get, like, where are the videos for the next week? So we upload it, but we don't announce it. So, like, just subscribe and like you will have notifications. Okay, so okay, and there were a few other things which probably I mentioned even in the ML class. Like, so these are based on the anonymous feedback that some of you are providing in the Moodle. So if you are not aware of this option, like, you can go to Moodle and there's an anonymous Google form where you can give feedback about the lectures. Okay, so I will just address some of the most common feedback. So one, I swipe things too fast, which makes it difficult for you to write. So I will try to be a little bit slow, like, and I will try to write in the same page as much as possible. But sometimes I have to swipe because, like, well, this is like a finite page. I have to move, and sometimes I have a figure in the next page. So maybe whenever I'm swiping, I will try to give few seconds before I swipe so that you have some time to take notes. That was one, and oh, especially for oral course, like, I received a couple of feedback that I'm too fast. So some people say I speak too fast, but some people say the lecture itself is paced at a very high speed. So today I'm trying to, like, do it slow. So give your feedback again, like, after the lecture, like if it was too fast or too slow. Okay, so I reduced the content for today's lecture so that we don't go too fast. Okay, so let's see how it goes. Okay, so let's begin. Well, given that it is once a week course, like, we need some reminder for what we have seen so far. Like, and it really helps if you at least read the lecture notes of the previous week. But we will do a very quick recap. So I think last week we discussed mainly about dynamic programming, right? So the basic idea or assumption in dynamic programming is, like, you have access to the transition probability or the transition dynamics, or in general, like, you have access to the dynamics of the world. which is basically P of S dash R given S comma A, right? So it's a pretty big assumption because like in most of the real life problems, you don't have access to this probability distribution. Like, but if you have access to this probability distribution, then dynamic programming gives you an efficient way of solving the MDP. And we discussed two main algorithms to do that, right? Like, so one was policy iteration. And we also discussed the extreme form of policy iteration, like which was value iteration. Right? So in both policy iteration and value iteration, like, well, in general, like for this whole family of dynamic programming approaches, like there was like one theme, right? Like, so in general, like there are two things that are happening, like simultaneously or like back and forth. Like, so the first part is policy evaluation, right? So where given a fixed policy, we are interested in finding V pi or Q function, like whatever value function you want, right? Then we had policy improvement, which is basically given the V pi or Q pi, like whatever you care about, find pi dash such that pi dash is better than, or like at least better than, like better than or at least same as pi, right? So now we discussed both of them separately. Like, so for policy evaluation, like we discussed how to do it in an iterative fashion, like by using the Bellman updates. And for policy improvement, like we also discussed policy improvement theorem, which says that whenever you act greedy with respect to a Q function, you are bound to improve the policy, right? So now once you have these two pieces, now you can put together these pieces. Like, so you could start with some arbitrary policy, okay? So let's just call it pi star, pi 0, okay? Now you do policy evaluation, you're going to get V pi, right? So then you do policy improvement, you're going to get, sorry, this is V pi 0, you get pi 1, right? So then you repeat this process, like, so you do policy evaluation again, you are going to get V pi 1, you're going to do policy improvement again, so you're going to get pi 2, and so on. So finally, you will converge, if you do this process again and again, like you will converge to pi star and V pi star, then it becomes pi star. Like, so you, at this point you converge. Like, so you do policy evaluation, there is no improvement. Policy evaluation and policy improvement, there is no change, right? Like at this point you converge. So this was the general idea, okay? And we looked at two specific instantiations of this idea. Like, so the first instantiation was policy iteration, right? Like, so in policy iteration, you first do policy evaluation, okay? And then you do policy improvement. Now, we also discussed that policy evaluation itself is an iterative process. So probably you're going to take a lot of epochs, a lot of iterations to converge to policy, like a good policy, like to the actual, to a decent like value function, and then you do the policy improvement, then you repeat, right? Like there is a for loop inside the for loop. Now, the question that we asked last week was, can we do better than this? So one thing that we realized is, in general, like anyways, for policy evaluation to converge, you have to do infinite number of steps. Like, and we are anyway truncating it at some point, right? Like, so then why not truncate it as early as possible? Like, so like an extreme version of this algorithm is like when you do only one round of policy evaluation and then you do improvement. Then you do another round of policy evaluation and then improvement, okay? Now, when you do only one round of policy evaluation, you can actually mix or merge the evaluation and improvement. So that is when you get the value iteration, right? Like in the value iteration case, like you have only one loop, and this equation kind of combines both policy evaluation and improvement. So the max part is policy improvement, and this is the policy evaluation side, right? Like so, like in policy evaluation, you consider all possible actions to update, but in policy iteration, but in value iteration, you only consider the max action, so that you're kind of like skipping like the steps and like directly do the policy improvement, right? So I think this is where we stopped. Any questions so far?
I have a quick question.
Yeah.
So, I'm kind of new to dynamic programming.
Hmm?
So, is it the fact that value estimate depends on the next state's value estimate is what it makes dynamic programming, or the way you implement it?
Yes. Yes. So, well, typically when we say dynamic programming, it means reusing some computations, right? Like, so in this case, like you are kind of bootstrapping your current state's value estimate.
It's more because of the Bellman equation.
Yes. Any other questions? Okay, so now I want to talk about how practical it is to do these kind of policy iteration or value iteration algorithms, right? Like so now for small problems like how your assignment problem is probably too small, but for a lot of small problems like where you have like let's say million states, like which is not small but like decent size, right? Like so you can easily do policy iteration or value iteration, okay? But there are a lot of interesting and like practical problems where the number of states is just too much. In that case, this naive version of policy iteration or value iteration that we discussed is not going to be that easy to be applied, simply because it has this for loop over all possible states, right? So both value iteration and policy iteration loops over all the states. If you remember, like we discussed about sweeps, right? Like so these algorithms work by sweeps. Like so, like let's say you have a bunch of states, like you sweep through all the states once, that is your one iteration, and then you sweep through them again, and so on, right? Now what if it's going to take you many years to just sweep through once, right? Like so I can give you an example. Like so I think this is the example that we see again and again. Like so in the case of backgammon, right? So you have 10 power 20 states, okay? To do value iteration with backgammon is going to take you thousands of years if you do the computations, okay? Now, which means like it's not very practical, right? Like so now one question to think about is like how can we scale up policy iteration to something which has 10 power 20 states, right? Like so if you have to do policy iteration for something like backgammon, like so how would you go about it?
You check for good actions or actions that seem.
Sorry, can you repeat, please?
And you check for the actions that already seem good and skip some.
Okay, so check for actions or states that you have already seen. Okay, yeah.
Can you try to target the states that happen the most often?
Yeah, so I think they're both similar answers, right? Like so the answers here. Okay, so there are a couple of questions in the chat. I'm going to reply after finishing this answer. So there are a couple of answers here, right? Like so the answers are focus on the states that you're going to visit more often, right? Like so when you play the game of backgammon, maybe there are like millions of states which you will never visit because they don't make sense for humans, right? Like so there's going to be like too many possible combinations, and like let it be backgammon or chess, right? Like so when we play, like so like we are going to see only a fraction of the states, and like for maybe for our entire lifetime. Okay, so then does it really matter if I have good policy for states which I will never visit or states I'm going to visit very rarely, right? So So this kind of gives us an idea for like how to improve value iteration and policy iteration. So there are a lot of asynchronous dynamic programming methods. Okay, so where the idea is basically just update whatever state that comes to you next. Okay, don't worry about sweeping over the state. So let's say this is my state space. Okay, so instead of sweeping over it, I will start interacting with the world. I see a state, I update its value, like value function. Then I see this state, then I see this state, then I see this state, this state, this state. Okay, so probably it might be the case that for this particular environment, I will rarely visit this region. Okay, so if I'm just visiting these regions, like then I could just update these places again and again, and I'm going to get a really good value estimate for these states, like a group of states which are more frequent. But I might have really bad estimates for states which I have never visited, but probably it doesn't matter, right? So now this idea of like using agents experience in the MDP to update values, right? So this is going to be one of the central ideas that we will exploit in every algorithm that we are going to see in this course. Okay, so because we should realize that in the beginning when I defined what is reinforcement learning, like I told you that it is about coming up with this function, like or learning this function which maps every possible situation to an optimal action, right? Like so now we can slightly refine our definition. Like so we don't care about, well, in some cases you care about every possible states, but most often you don't care about every possible states and their optimal actions. Like what you really care about are states that you visit often, or states which are very common, like on day-to-day basis for you, and like you want to make good or optimal actions in those states. Okay. Now, in this case, like we are using the agent's experience, okay, to decide what state to update. Okay. Now, there is also a little bit of caveat here which you should be aware of. Like so, when you're using agent's experience to decide what state to update, then exploration is a bit of a problem. Okay, because the next state that you are going to visit is going to be dependent on your value estimates, right? Like so your latest value and policy info from your DP, right? So that is going to guide the agent's decision making. Okay, so which means unless you don't have a good exploration policy, you might visit 10 states and do some estimates and then say, oh, this is the best state, right? And you will keep repeating, like you keep visiting the same state again and again. Like, or in other words, unless there is an external force, you might get stuck in a local policy and you are not aware of the fact that there are better options out there. Okay, so this is something to keep in mind. So probably I'll answer the questions in the chat. So there are a lot of good questions. Like, so do these algorithms work for deterministic policies only or also for stochastic case? They should work for stochastic case as well, like, but we are not discussing the stochastic versions yet. So we are still considering deterministic policies, but for today's lecture, we are going to go towards stochastic policies. So what is the time complexity of value iteration? So that's a good question. So that is what I will finish the topic with. So we will talk about time complexity in 5-10 minutes. Would modeling dependence or correlation between states be useful to update states without choosing some of them? That's a very good question. So the question is, can we model the dependencies or correlations between states so that by visiting just one state, we can learn about other states. Okay, so that is the idea behind function approximation. So probably in like 3 more lectures, like so we will talk about like how to do such function approximations and combine them with the algorithms that we are currently seeing. Okay, all good questions. Okay, so now I want to talk about this idea of like doing policy evaluation and improvement like back and forth, right? Like so this general idea of doing back and forth evaluation and improvement is known as generalized policy iteration, okay, or GPI. So as we will see in the next few lectures, almost all reinforcement learning algorithms kind of try to do generalized policy iteration, okay, but in different ways. So now this generalized policy iteration consists of like 2 simultaneously interacting processes, as I mentioned before. So there is the first process, which is policy evaluation, okay. The goal of policy evaluation is to make the value function consistent with the policy, with the current policy, right? So I have a current policy. I want the value function to be up to date for this. That is policy evaluation. And then we have policy improvement, right? So which makes the policy greedy with respect to the current value function, right? And these 2 processes interact. So we have seen how it interacts. Like, so you have some policy, you do evaluation, and you get the value function, right? So in the case of evaluation, like you want the value to go as close as possible to the value of this policy. So then you have the improvement process where you want the policy to go as close as possible to the greedy policy of me, right? You repeat this again and again. So eventually you will reach the scenario where you have obtained, like you have found the most optimal policy and value function, right? So now, so what is interesting about this idea of generalized policy iteration is it's kind of like 2 processes which are both competing and cooperating, okay? So it's kind of competing because the value function like always tries to, okay, then maybe it's easier with the diagram. So now, let's say, so you have a value and a policy, right? So now, given some policy, like you find a value, right? Like, so the value moves a little bit, okay? So then the policy improvement scenario pulls back the value by constructing the greedy policy, okay? So then the value policy evaluation, like again, moves in opposite direction. So they kind of move in opposite direction. But what is interesting here is like, so they are both not completely opposite, okay? So like in some sense, like the analogy that the book gives is like, they are kind of 2 lines which are not parallel, okay? So at some point they have to meet. So you do this policy iteration and evaluation, like sorry, policy evaluation and improvement again and again. They kind of try to move from each other, but the gap reduces as you reach the convergence. And eventually you will reach the case where you have found V star and pi star, and then you just don't move, okay? So this is a very robust framework to design algorithms, okay? Now you can think about any way in which you want internally evaluation and improvement, like as we discussed before, and almost all of them converge to the optimal policy, okay? Well, of course, like you have to prove that. We are not going to prove that in this course, like, but in general, like generalized policy iteration converges, yeah?
So this like sort of path here that's moving around in like the space of value functions or something.
Sorry, can you please repeat?
So this like kind of path here, like this sort of gradient update path is like moving around in the space of like value functions. Like what is the space here? Like what is the geometric?
Well, it's the joint value and policy. Like so, like you have you have value functions and you have the policy, right? So you're trying to update both the value function and policy.
Is it more like the estimates, how confident you are about the estimates or something? Because when you do a value estimate, you're more confident about them, but when you do a policy estimate, you again drop down the confidence.
Well, it's not about confidence. It's more like you have a policy, okay, and you compute the value estimate, okay. Now, this value estimate is consistent with the policy, right? Well, usually not, because we don't finish the policy evaluation. But the hope is, you get closer to being consistent, right? So even before you reach that consistency, policy improvement is pushing you away to other direction by doing the greedy policy, okay? Now, again, policy evaluation tries to be consistent with this new policy, but policy improvement doesn't let it do it, right? Because we don't complete the policy evaluation. So every time the policy evaluation is trying to get better and better, policy improvement kind of tries to make it a little bit bad, because like it is improving the policy as well. But the point is, eventually they should both agree at some point. Otherwise, they are going to keep doing this process, right? So when they converge to optimal policy, because there is no more improvement possible, and you have value function which perfectly aligns with the policy. Okay, yeah.
So intuitively, how is like making the value function more consistent with the greedy policy pulling? So like if you think about like a geometric space and you have like you're going down a greedy policy path, if you just follow a greedy policy path, obviously you're not going to converge to an optima. So like how is making a value function consistent with a greedy policy pulling it back from being the bad path just going down?
Okay, so
I mean, obviously you can't keep going down if you're not changing the value function, but intuitively, like
yeah. Okay, so well, these are kind of hand wavy arguments, right? So like when you do policy evaluation, you want to be consistent with respect to the policy, but in practical situations, like you don't do that, because you just do one step, or sometimes even you don't finish one step if you're doing asynchronous DP, right? So like you move in some direction, and then policy improvement gives you a new direction to move, because the policy has changed. Now you try to move to this new direction, okay? So that is what is happening here. Like, so you're trying to move in this direction, okay? Before you finish moving, like policy improvement changed a little bit. So you have to move in opposite direction. Like not opposite, maybe I'm using wrong words here. So you have to move in a different direction. Now, policy improvement kind of forces policy evaluation to keep on moving, right? So now at some point they have to converge. Like, so when they converge, they are in optimum.
yeah, that makes sense. I guess my intuition is just if you're making a value function consistent with an already greedy policy, it would somehow, my intuition is it would somehow keep going away from an optimum.
Yeah, but
basically go in a similar direction.
Yeah. Oh, no, that. Yeah. I think, but we don't do that here. So, so it's kind of an elegant algorithm, because you're doing a lot of approximations here. Okay. Like what is interesting here is like even with all the approximations, you're going to converge. Okay. Okay. So now let's talk about the efficiency, like about the complexity question, right? Okay. So dynamic programming actually finds the optimal policy in time that is polynomial to the number of states and actions. Okay, so let's say n is the number of states and k is the number of actions. Okay, now can somebody tell me how many possible policies are there?
And to the power of k.
Is it n power of k?
K power n.
Or k power n? It's k power n, right? So you have k power n deterministic policies. Oh, by the way, deterministic policies. We are still like if you have stochastic policies, then you have probably like way more than this, right? Like so, you have at least, well, you have exactly k power n deterministic policies which are possible. Like if you have n states and k actions. Now, imagine you are doing direct search in these k power n. Okay, it's going to take you lots and lots of time to figure out the right policy. Okay. On the other hand, like dynamic programming, even though we complained in the beginning that it is a computationally expensive approach when compared to other approaches we are going to see in today's lecture and next week's lecture, they are still way more efficient than direct search. Like, so they find the solution in polynomial time. Okay. Now, one can, as I mentioned before, one can also use linear programming to solve MDP, but they are not as scalable as dynamic programming. So there are still a lot of applications where people are using policy iteration and value iteration. So these are situations where you have access to the dynamics function so that you don't need to learn from experience. Okay, so probably we will stop our discussion about dynamic programming here and get started with the next class of algorithms, which is the main topic for today's discussion, like which is the idea of Monte-Carlo methods. Okay, so there is a question in the chat. What is the memory complexity? Well, I guess memory complexity is number of states. Sorry? What?
For the first one, but the dynamic is.
For both policy iteration and value iteration, you basically store values, right? So it's just the number of states. You can have two arrays if you want, but we often do in place. Okay, so let's get started with the next class of reinforcement learning algorithms, which is Monte-Carlo methods. Okay, so far we were doing dynamic programming where there was not a lot of learning involved. Okay, so if you think about it, we had access to the dynamics function and we were mainly estimating the value function or policy, right? So we never interacted with the world in the case of dynamic programming. So given that you have access to the transition function, like you can do value iteration or policy iteration, find the optimal policy and directly deploy it in the real world. Okay. However, there are many situations where you don't have access to the dynamics function of the world. Okay. Now, in that case, the only way to learn is by learning through interaction or learning from experience. Okay. So then the question that I want to ask here is, can we directly learn the value functions from experience? Okay. Now, we have already seen one way to learn the value functions from experience. And someone tell me when and what was that?
You said you were only updating a few states.
No.
Epsilon.
Well, that's kind of true, but.
Greedy bandits.
Sorry?
Greedy bandits.
Bandits, right? Like, so in bandits, we already discussed in detail about how to learn value estimates, but in that case, like it was not a state value because there was no state in bandit, like it was just an action value, right? But we did discuss several algorithms for like value estimation by interaction, right? So now we are going to develop similar algorithms for the full reinforcement learning problem. So when I say experience, right? So it could be two types of experiences. It could be the actual experience, okay, which means you are interacting with the real world, okay, or it could also be simulated experience. Okay, like for example, let's say you want to do self-driving cars. Okay, you definitely don't want the self-driving car to learn from actual experience from scratch. Right? Imagine you have a car which is learning how to drive by itself on the road with other passengers in the road, right? Like on the road, right? Like so, you're going to see a lot of accidents, right? Like, and the car would damage, and probably you should use millions of cars before you learn a policy. So the point is, like, there are a lot of situations where directly learning by interacting with the real world is dangerous or not safety or simply not possible. Okay. So in those situations, like you're kind of bound to learn from simulation. So when I say learning from simulation, that requires access to the model of the world, right? Like then how is it better than dynamic programming? So there is a big difference between dynamic programming and learning from simulations. Okay. So in the case of dynamic programming, we need access to the probability distributions of the next state and the reward function. Okay. Now, on the other hand, for learning from simulations, all you need is some model of the world which will sample the next state for you. Like given a state and action, will tell you what is the next state. You don't have access to the probability distributions in this case. Okay, so in this case, no access to probability distribution. Okay, so there are actually many situations where this is easier. Like, so for example, let's say you want to simulate some physical settings, like you have a lot of physics simulators available, like and even for self-driving cars, like there are a lot of simulator environments available, like where you can train your reinforcement learning agent to drive, and then you take this policy and deploy it in the real world. Okay, now there are a lot of challenges in moving from simulation to real world. So I'm not sure if we will talk about it in this course, but I can, like, if you're interested in that kind of topics, Liam Paul at UDM, like, is teaching like an autonomous vehicles course, like where I'm sure they talk a lot about how to learn from simulation and move to real worlds. Okay, so now what we are going to see now is like how to learn from experience. This experience could be actual or simulated. Okay, so the technique that we are going to see is, the first technique that we are going to see is the idea of Monte-Carlo return. Monte-Carlo methods. Okay, so you might have seen Monte-Carlo in different courses, like in different time of your undergrad or grad school, right? Like, so in general, we use the word Monte-Carlo whenever there is a random quantity that we are estimating. Okay, so in this case, our random quantity is the value functions. Like, so like we are estimating the values from sample returns. Okay, so the idea here is we are going to solve the oral problem. Okay, solving oral based on averaging sample returns. Okay, in some sense, that is what we were doing even for bandits, right? Like, we're going to do similar things, but for reinforcement learning. So we will see what are the challenges. Now, for the discussion of Monte-Carlo methods, like, we are going to assume that we are in episodic setting. Okay, because I told you that we are going to average from sample returns, right? Like, so to compute the return, the episode should terminate. Like, if the episode is not terminating, it's going to be difficult for you to compute the returns. So for this class of family, like this family of algorithms, we're going to assume that the episodes always terminate at some point. So what we can do is we can start interacting with the world. Whenever the episode ends, for every state that we have visited, we compute the return. Okay, the sample return. Now, similar to bandits, you can just keep track of these sample returns, like combining them in a list, and take an average. Now, this average is going to be the value estimate for this state. Is it clear? Any questions here? No. Okay. Now, this is kind of similar to reward estimation in bandits, right? Now, even though they look like similar things, there are a lot of differences. Okay, so we have bandits, and now we have Monte-Carlo for oral. Okay, so in the case of bandits, we were trying to estimate the rewards, right? But in the case of Monte-Carlo methods for reinforcement learning, our goal is to estimate the returns. So what is the difference between reward and return? Somebody? Yeah?
Reward is instantaneous and return is long term.
Yeah, so reward is instantaneous, right? Like, so return is kind of cumulative, like from current state to the end of the episode. So these are two different entities, okay? Now, in the case of bandits, there was no concept of states, right? Like, or in other words, there was only one state involved, right? So you're doing really one estimate. Like you're doing estimates for only one state. But in the case of oral, there are many states. Okay, which means you have to do these action value estimates or state value estimates for all the states in the reinforcement learning problem, right? Now, one naive way to do this is to treat each state as an individual banded problem, right? Like if you consider each state to be an individual banded problem, then you can do value estimates for them separately using any of the bandit algorithms. Like, and we also discussed contextual bandits, right? Like, which is kind of similar to that. Like in the case of, if you remember, okay, maybe another question. So can somebody tell me what is contextual bandit? Like, so or how is it different from reinforcement learning? Maybe somebody from the back or the Zoom call. So what are contextual bandits? Okay, I want a different voice. Anyone? Yeah?
Add selection of some of contextual bandit examples.
Okay, but what are contextual bandits?
It depends on the context. Let's say it depends on the context.
Okay, so well, maybe I'll rephrase. What is the difference between a bandit and a contextual bandit? Right?
So if you have like 10 settings of different bandits and each one will have a different reward distribution, then
okay. Okay, so in some sense, like contextual bandits have many states, like reinforcement learning, right? So they have many states, and you're kind of doing action value estimates for all these states simultaneously, right? But the big difference between contextual bandits and reinforcement learning, or Monte-Carlo for reinforcement learning, is the fact that in contextual bandit, you take an action that is not going to affect what is your next state, okay? But in the case of reinforcement learning, you take an action and that is going to affect your next state, okay? So in some sense, these are related or interrelated bandit problems, okay? Now there is another complication here. So the return that you are trying to estimate, right? It is not, okay, let's take some state yes, okay? You're trying to estimate the return for, let's say, a state action pair, okay? So Q of S, A. You're trying to estimate, maybe to make it even more clear. So let's say I have an S1, I take A1, I go to S2, comma R2, okay? Then I do A2, it goes to S3 R3. I take A3, it goes to S4 or 4, probably let's say it stops here, okay? Now, I'm trying to estimate Q of S1 A1, okay? Now this return from state 1, right, is not just dependent on the action that I take in state 1. It actually depends on the action that I take in state 2, state 3 as well, right? Because return is actually the sum of all the rewards, right? Like, so in this state, I might take an optimal action, but if I take a suboptimal action in the next state or any of the future states, I'm going to get 0 reward or like bad rewards, which means my return is going to be affected. So what is more challenging in reinforcement learning is the fact that the future states and the actions that I take in future states are going to affect my return, okay? Now, as we attempt to do here, like, so we are trying to, as we attempt to do here, like we are trying to estimate the action values for all the states simultaneously, right? Which means for state 2, in the first iteration, I might have one action that I think is optimal. And my return is going to be based on that. But in the next iteration, my notion of what is optimal in state 2 is going to change. And this notion is going to keep changing as I'm learning, okay? Now, which means this return that I'm trying to estimate, right? So that becomes a non-stationary target.
Is it based on the exploration strategy that it will become better. Not
Yes, it is based on the exploration strategy, but even without exploration strategies, right? Like, so you are trying to estimate values for state 1, state 2, state 3, state 4. The problem is state 1's estimate is kind of conditioned on like what happens in state 2, state 3, state 4.
if you have enough number of episodes,
Yeah.
won't it
Oh yeah, eventually it goes there. Yeah. So eventually, like when these estimates converge, like you do stabilize, okay? But what I'm trying to argue here is this is a very challenging problem than action value estimation in bandits, okay? It's challenging for several reasons. One, there are many states and they are interrelated. This interrelatedness makes the problem non-stationary, okay? So now this non-stationarity is like very common in all the reinforcement learning algorithms. Like, so like most of the algorithms like are going to struggle with this non-stationary or moving target. Okay, so what I thought would be the estimate of return for state 1, okay, in the beginning of the training is going to continuously change, because as other state action values get better and better, this return might actually improve. So which means I thought 5 is my return from the state, but then I discovered that actually it's 7. So then I discovered that it is actually 10, right? So that makes this problem non-stationary, yes?
So aren't like Q function associated with policies?
Yes.
So I think that's why the things are changing, right? So like you're at the same time trying to change the policy also.
Oh, that is true, but my arguments hold even for state functions, but they are also dependent on policies. Oh yeah. Oh, okay. So when I say estimates change, right? Like it implies policies are changing. So yeah.
Also, won't it make more sense to just say that for this particular sequence, I have a return rather than saying like calculating for each state?
Okay, so that's a bit involved question. So the question is, instead of estimating the value function for a state, why don't you estimate value function for a sequence?
For an episode.
Or an episode, okay. That's an interesting proposal, but there are a lot of challenges there, right? Like, so now there are like many possible episodes. Like, so like now how would you?
How many episodes are you calculating?
Yeah. So it's going to be a bit challenging.
What I'm saying is,
but there are smarter ways of doing what you are saying.
you're essentially, instead of like making a better estimate function, you're kind of talking about a better return for the episode. So it improves because you're taking a lot of samples, but it is not making the like you're not considering all the actions in a state, so that's not making it better in the returns.
Well, I see your point, but it's a bit more complicated direction to go towards. Like we will like kind of move towards the direction towards the end of the course, like when we talk about hierarchical reinforcement learning, like so where instead of trying to estimate how good is an action, we will estimate how good is a series of actions or a sequence of actions. So that would go close towards what you're saying, like, but that's probably way more advanced or in the future for current discussion. Okay, so I guess you get the idea of like the difficulty of estimating action values for reinforcement learning, like through experience, right? Like, so now probably we'll take a break here, and after the break, we will talk about how to actually do it. And as usual, we will start with prediction, which is evaluation, policy evaluation. Then we will do improvement. Then we'll combine together so that we have a control algorithm. Okay, so we'll take a 10 minutes break.